Um, Good morning. Can everybody hear me? Okay. My name is Melanie Walling, and I will be presenting a similar sensitivity results of hazard for ground motion prediction equations, and this is for the Palo Verde Nuclear Generating Station. For my presentation today, it's primarily broken into two pieces. One is to just go over the base case hazard. This gives you a background, so you know which sources are contributing the greatest to hazard. I'll be presenting results for PGA at the annual frequencies of exceedance at 10 to the minus 4 and 10 to the minus 6. I'll also be presenting it for a low frequency, which is 1 hertz, at just 10 to the minus 4. And I'll give you my reasons for not presenting 10 to the minus 6. It's very similar to 10 to the minus 4. Once I go over my background, and I kind of want you to understand, I'm hoping that this background will put you in context to how to interpret the results. I'll be going into the sensitivity results, and I'll be presenting them for, again, a high frequency of PGA at 10 to the minus 4 and 6, and then at 1 hertz at 10 to the minus, actually that should be 10 to the minus 4. Just to go over it as a little background, here's a map. This is the site of Palo Verde Nuclear Generating Station. This is a map of the faults that went into the base case for the hazard sensitivity. For the hazard, we're looking at up to 400 kilometers, and these are the major fault contributors to Palo Verde. Actually, the major contributors right here is Sierra Prieto, and I'll be showing you results primarily which the Sierra Prieto is responsible for. So for the base case hazard sensitivity, we had these faults, and then we also had background sources. Again, this is a map. Here's Palo Verde Nuclear Generating Station, and these are the 5 different background sources that went into the base case hazard. This one right here, which the Palo Verde resides in, is the host source, and then this is the basin and range, called the basin and range. So both the faults and the background sources went into these results that I'll be showing. For the base case ground motion prediction equations, we have the 5 NGA models, which have already been talked about. They're also equally weighted, and with the site condition of 760 meters per second. So to begin with, here is the hazard contribution by source type for PGA. On the y-axis is the annual frequency of exceedance, and on the x-axis is the spectral acceleration from 0.01 g to 1 g. The solid black line is the total hazard curve, and the solid red line is the contribution to the total hazard for fault sources, and the solid blue line is the contribution to the hazard curve, to the total hazard for background sources. So for our talk, this is where hazard we're concerned with in the range of 10 to the minus 4 through 6. And we'll be focusing on what's going on in the hazard curves for here. So at 10 to the minus 4, you can see that the fault sources are the primary contributors for PGA. And that at 10 to the minus 6, it switches to the background sources. And this is why I'm showing you both results from the 10 to the minus 4 and for the 10 to the minus 6. For 10 to the minus 5, they're about neck and neck for a fault contributing. Looking at the hazard deaggregation at 10 to the minus 4 for PGA, this is what it looks like. It's about a magnitude 7.2 at 220 kilometers, and it's the Sierra Prieto fault, which has a strike-slip fault mechanism. Moving on to 10 to the minus 6, where now the background sources are the major contributor. You can see that that it's primarily in the small distances and smaller magnitudes where we have an earthquake of magnitude 6 and a rupture distance around 20 kilometers. And this is the host source, which has a normal fault mechanism. So at PGA, there's a few different things playing around. And then for the host source. Moving on to now 1 hertz, here is a similar hazard plot where we have the black line again is the total for 1 hertz, and the red is the fault contributions from the fault, and the blue is the contributions from the background sources. So you can see here that at 10 to the minus 4 and 10 to the minus 6, it's primarily the faults who are contributing. And hence, I'm not going to show my results for 10 to the minus 6 because they're very similar to 10 to the minus 4. If we look at the main contributors, here is the fault source hazard contributions broken out by different fault types or the different faults that contributed. The red line is the total hazard. The pink line is the hazard contributed from the fault sources. And then these other dashed lines are the source contributions from the different faults. And so if you sum up these dashed lines, you get the pink curve. And if you look at 10 to the minus 4, the major contributor is the Sierra Prieto fault. And that occurs also from 10 to the minus 5 to 10 to the minus 6. So at 1 hertz, you can see that Sierra Prieto is the predominant source contributor. So now what I'd like to do is put these results of the source contributions into context with the results that I'll be showing for the hazard sensitivity. So we know that for PGA at 10 to the minus 4, the Sierra Prieto is pretty much the predominant one, and it's the faults. At 10 to the minus 6, we have the background sources that are the primary contributors, the host source, and also at 1 hertz. And then if we look at the deaggregation, this is deaggregation, which just shows that it's a Sierra Prieto at 1 hertz. So now I'll be going into the hazard sensitivity. This is similar to what Nick, who was shown. Actually, I stole it from Nick. Just to go one more time to go over it, just because it's kind of hard to get the first time. The sigma is the median base case, so we have those 5 NGA 2008 models with the sigma for the unique GMPE, the results. The sigma VSS is the single station sigma, and again, we're looking at the median base case, but now we've adjusted it for a single station sigma, and we're looking at it with its GMPE sigma. The next one is the individual GMPEs, and that one's the most straightforward because it's just the GMPE with its own sigma. And then we have the GMPE median, which is the GMPE with its fixed, with the sigma fixed. And the reason why the sigma was fixed is because by fixing the sigma, we're able to see if the differences in the models are more due to the median or if they're more due to the sigma. I'll also be showing you results for strike slip, where for the base case I have for the normal sources, and then for the individual GMPs, it's the strike slip results, or for the strike slip results, it's the GMPEs. For the strike slip medians, it's similar, but the sigma is again fixed, and the same goes for the normal faults, where I have my base case as my strike slip sources, and I'm looking at comparing the results from the normal sources with those strike slips. And for the medians, the sigma is fixed. Okay, so now I'm going to be showing you results for PGA at 10 to the minus 4 and 10 to the minus 6. Starting with 10 to the minus 4, here's what a similar plot to what Nick showed. It's a little bit difficult to see. These are the results, and we can see that we have this sigma all the way down to the normals. And it's a little difficult to see, so I kind of blew it up a little bit for you guys. So here's sigma, and here's sigma VSS. Now, and what you can see is that the 2008 models cluster together as is expected around 1. For the sigma, this is because this is our base case. And we can see that this is the second line that Nick was talking about, and this has our NGA West 2013 models. This third line around here is the Grazer-Kalkin, the Zhao model, the Acker et al. Model, and the Bindi model, and then this is the average. So this is the results from the sigma, and this is the results for single station sigma. So one thing I'd like to point out here is, which I think is really important is how to interpret these tornado plots, is that the closely spaced, the models congregating together, doesn't mean that there's a lack of uncertainty. It just means that the models are agreeing with each other. So some people can look at the tornado plots and they think about, well, close distribution means that there's a lack of uncertainty, but that's not true. These results should be taken into the context of how much data went into developing these models. Because if only a few data points went into developing these models, the models are going to have a close agreement. But that doesn't mean that there's an uncertainty. It just means that there's just little data to constrain the models. So that's one point. So I have these just a little note just to point that out. So what you can see here is that at 10 to the minus 4 for PGA is that the distribution from the NGA West 2000 has actually increased relative to the 2008. Well, so what does this mean? So what this means is that as we have, what was it, 20,000 data points that were used to develop this in around 3,500. It means that as we had more data, is that the uncertainty didn't decrease, it increased, or the epistemic uncertainty. So this is just implying that there was a larger uncertainty that the 2008 models just never captured by having a larger distribution. And then what you can see here is that moving on to the single station sigma, is that most of the points lie less than a ratio of 1. And this is just because you have a reduction in your total sigma, which would mean you get a reduction in your ground motion. So those results make sense. This is now moving on to the GMPE and the GMPE median. PGA, you can see that there's a larger dispersion for the 2008 models, but now there's a smaller dispersion for the 2013. So this tells me that the models are now having a closer agreement. As more data came in, more of the models are coming closer together, and the uncertainty is now decreasing. And then what you can see here is for the median GMP, everything's been shifted to your left, and that's just because when you constrain the median, when you constrain the sigmas to 0.65, the ground motion amplitudes dropped. So these ground motion amplitudes are a little bit larger. Looking at strike slip, if you can remember, it's the Sierra Pareto is my controlling source, and it's a strike slip source. So these results should be taken in the context of that this is where most of my hazard is coming from, is the strike slip sources. And you can see that there's a large dispersion. And then for the 2008 models, and it's decreased quite a bit with the 2013 models. So we're seeing more of an agreement between the models as more data came in. And then for the median strike slip, it's just shifted over, and that's primarily because of sigma. For normal faults, here is the tornado plot. So this is what I was wanting to point out about why it should be, it's tricky to interpret the tornado plots, is that for normal faults at 10 to the minus 4, it's not a huge contributor to the hazard. So most of it's for strike slips. So one reason why all the points are falling in line with each other is that my normal faults aren't huge contributors, and people might look at this and interpret that there's a lack of or that there's a strong agreement or low uncertainty in normal faults, but we know that's not true because there's not much data of normal faults in the database. So this shouldn't be considered as a lack of scientific uncertainty. Okay, now we're moving to 10 to the minus 6, so similar plots. I'll move a little bit quicker. At 10 to the minus 6, this is now my controlling source is my normal fault. It's my host source, so it's a magnitude 6, close in distances. So the results have the distributions have changed a little bit. I still have a close agreement with the 2008 models. And the 2013 models for the NGA West have increased relative to the 2008, but the dispersion hasn't for the normal faults, close in distances. And then for the single station sigmas, it's less than 1. The ratio is less than 1, which is expected since you're having a smaller sigma, total sigma. Here's for the median GMPE. And what you can see here is that the dispersion, again, for the 2008 is much larger than the 2013, which, one question is that because there's just a greater agreement now with more data. And also for the median sigmas, or the sigma lockdown at 0.65. Strike slip, you can see that at strike slip, it doesn't really contribute at 10 to the minus 6 for PGA, and that's why they're aligning on top of each other. But normal faults do contribute at 10 to the minus 6 for PGA, and so you can see now that there's more dispersion, more in the 2008 than the 2013 for both normal and when the sigma's locked down at 0.65. Okay, now I'm shifting and I'm going to show you results just for 1 hertz at 10 to the minus 4. This is where strike, it's a Sierra Pareto is the major contributor here. So it's magnitude 7 at 220 kilometers. So one question is how well the GMPEs are constrained out at that distances. Nick talked a little bit about that. And you can see that, that there's a relatively decent agreement with the 2013 models, but it's greater than the 2008 models. Here is for the GMPEs. You can see that there's quite a large dispersion in the agreement between the models. And it doesn't look like the dispersion has decreased at all from the 2013, from the 2008. It's just shifted to have lower ground motions for the GMPEs at the longer distances, larger magnitudes. Here is for strike slip, which is the primary source contributor. And you can see that, again, there's even a larger dispersion. And the dispersion hasn't decreased from the 2013, it's just the ground motions have just decreased from the 2013 models. And then here's for normal, but normal doesn't contribute at 10 to the minus 4 at 1 hertz. And here are my references. So any questions? Okay.